An algorithm is a step-by-step way to solve a problem. It gives you a path from a starting point to a result. In coding, that clear path matters a lot. Algorithms are not only used in programming. Recipes, maps, school routines, game missions, and recommendation systems all depend on ordered steps to reach a goal correctly. Your daily routine is already a real algorithm. Wake up, get ready, pack your bag, and reach school. The goal works because the steps happen in a useful order. Computers follow instructions very literally. If you give a vague command, they do not guess what you meant. They need clear, exact steps to do the job correctly. Humans are flexible and fill in missing details from context. Computers are different. They only do what the instructions say, not what the writer hoped they would understand. Good instructions are clear, specific, and well-ordered. Bad instructions are confusing, vague, or incomplete. That is why programmers learn to think carefully before writing code. Sequence matters because the same steps can fail if placed in the wrong order. A correct solution is not just about what you do, it is also about when. Sometimes the whole process fails because of one wrong step. That is a powerful lesson in logic. Small mistakes in planning can cause big problems in results. Many systems can be understood using input, process, and output. Something goes in, something happens to it, and then a result comes out. This pattern appears everywhere. Imagine entering quiz scores, calculating the average, and then showing the final grade. That is input, process, and output working together in a simple school example. Big problems feel stressful when you look at them as one giant task. Your brain sees the size first. That is why smart problem solvers break them apart. When you split a big challenge into smaller steps, the work becomes more manageable. Instead of thinking, build everything, you focus on one clear piece at a time. Small steps reduce pressure because each step feels possible. This is how coders, designers, and engineers handle complicated projects without getting stuck or overwhelmed too early. Logic means using rules to decide what happens next. A rule can be simple, like if homework is done, then you unlock game time or free time. Weather is a great logic example. If it is raining, take an umbrella. If it is not raining, keep moving. One condition changes the next action. Battery level also uses logic. If the battery is low, charge it. If it is high enough, keep using the device. Rules guide actions in everyday life. A decision point is where one path splits into different directions. This is a core idea in algorithms because many solutions depend on choosing the right next step. A login screen shows this clearly. If the password is correct, the user enters. If it is wrong, the user must retry. One check creates two outcomes. Simple yes or no checks power many digital systems. Discounts, permissions, access control, and account settings often start with very small rules that control bigger behavior. A missing step can break a full algorithm. Even if most of the plan is good, leaving out one important action can stop the final result completely. Unclear steps are dangerous because they create confusion. Instructions like make it better or do the thing are not useful. Strong algorithms must be specific and understandable. Testing means walking through the steps to see whether they really work. You check the order, the details, and the result before trusting the algorithm completely. Debugging does not begin only after code fails. It can begin in the planning stage. Fixing the thinking first often saves a lot of time later. Two solutions can reach the same goal, but one may take much longer. Efficient algorithms aim for a cleaner, faster, or smarter path without losing correctness. Repetition means doing similar steps again and again. Instead of writing or planning each one separately, you recognize the pattern and treat it as a repeatable action. Repetition saves effort because one reusable pattern can replace many copied steps. This idea becomes very important later when you learn loops in Python. Some algorithms combine decisions and repetition. You check something, repeat if needed, and continue when the condition is satisfied. That creates much more powerful problem solving. Games use algorithms constantly. Move forward, check for an obstacle, jump if needed, collect rewards, and continue. Behind fun gameplay, there is a lot of logic. Recommendation apps also use algorithms. They look at what you watched or liked before, then use rules and patterns to suggest what you may enjoy next. Homework planning is a great real-life algorithm. Check deadlines, rank urgency, choose what comes first, and work through tasks in a smart order instead of randomly. Shopping apps use decision logic too. If your total passes a rule, a discount is applied. If not, the price stays the same. Rules change outcomes. A chatbot also follows step logic. It receives a message, identifies what kind of message it is, and then chooses the most appropriate response path. Now you can build a simple algorithm yourself. Start with an input like a score, compare it with a passing rule, and show a result. Good problem solvers improve their algorithms over time. They remove extra steps, clarify weak steps, and make the path easier to follow without changing the goal. This chapter builds the thinking behind coding. You now understand sequence, input, and output, logic, repetition, testing, and improvement. That is how programmers begin before writing code. Chapter 3 is finished. You learned how algorithms work, why order matters, how logic helps make decisions, and how repetition makes problem-solving stronger. You also saw how testing and improving steps can lead to better results. Great job! You're building the mindset of a real programmer. Next up, Chapter 4, where we start writing your first Python program.